Okay. There's a correction. One of you pointed it out during the break. Apparently, if we focus the camera on this picture, I switched the roles of the plus and minus sets. This should be just the other way around. So this should be minus because this is a negative coefficient. This should be plus because that's a plus coefficient, so on and so forth. But the mechanics, they don't change. I hope. I hope. Well, I hope meaning that, if there's a mistake, you should point that out. That's your job, see? For me, it's the conceptual part that I should give. You work out the numerical parts. All right, how would we do this easier? Let's just work that out, and then I'll switch to some other topic. The efficient way to do the same example, let's say more efficient way. Let me change my colors back to black again. All right. My initial system involves x1, x2, z, and right-hand side b. I'm going to write the coefficients in a matrix, minus a1, minus 3, minus 1 for the first expression here, with z on the left. Okay? And the second expression is 1, 1, 0, and 6. Let's just separate the right-hand side out. The omitted ones are 0. Minus 1, plus 2, 8, minus 1, 0, minus 1, 0. So that's my matrix for the first system. Let me number the inequalities 1, 2, 3, 4, and 5. And I'm eliminating x1, so I'm using this column with pluses and minuses. Okay? In the second system, after the elimination, I'm going to have zeros for x1, something else for x2 and z, and the right-hand side. So this is what we're going to have. When I pair up 1 and 2, negative and positive should be paired up. Okay? One is a lower bound, the other one is an upper bound. So 1 and 2 give me the new inequality 1. And that has 0 for x1. The eliminated variable always has a 0 coefficient, minus 2 and minus 1. And the right side is 6. I hope that agrees with what we have here. Yes. And the next one, the new number 2, is the pairing of number 2 and 3 from the original. And you get 0, 3, 0, 14. How do we get these numbers? Let me illustrate that using the new pairing 2, 4. You look at 2 and 4. That's the pairing. One is a 1, the other one is a minus 1. You're multiplying this. Remember the formula I wrote down, in parentheses, aik times ai1, so on and so forth, minus the other one. So you're taking 1 times 0 and plus 1 times 1, because, what was the formula? aik, ai2 minus, what was it? Somebody tell me. Just look into your notes. AI1, sorry, AI1. AI1, AI2. This is for x2's coefficient in the second system. Hmm?
AK1.
And
This one was true.
what is this?
AK1, AI2.
AK1, AI2, okay.
Minus AI1,
AI1,
AK2.
AK2. This is all we're performing, plus the remaining ones, okay? This is constant and negative. This AI1 is already negative, so negative that, so that makes positive. So 1 times 0 in the pairing of 2 and 4, 1 times 1, that will give you 1 here. Right? Yeah. What about this one? 1 times 0, so that will be 0. And then 1 times 0, 1 times 6, that will be 6. That's what I've got. This is also 0. The last one is just the old 5. It becomes a new numbering, number 4 now. It's the same as the old one. The zeros, we don't write them down, so that's 0. Mm-hmm. For example, in obtaining number 3 here, look at row number 2. It will be, this is the pairing of 2 and 3. So 1 times 2 plus 1 times 1. That's how you get. It's easy to do it on the matrix once you master what you're doing. Okay? All you're doing is you're doing this operation from one system to the next one. All right, you've got this. And then when you eliminate the x2 variable in this system, the pairing of 1 and 2 from system number 2 gives you what? Minus 2 times 0, 3 times minus 1, that's going to be minus 3. And then minus 2 times 14, we're doing 1 and 2, right? Minus 2 times 14, 3 times 6. How much is that? 18 minus 14. Why is, okay. Why do I have that? I'm doing 1 and 2. Okay, let's see.
Minus 46.
Ah.
Direct 46.
It's 46, yeah. The next one is minus 1 and 18. This is the pairing of 1 and 3. And the pairing of 4 and 2. It's 0. There's nothing here. You've got 14 here. And 4 and 3, that's also 0 with 6 here. Does that agree with what we have here? It should. Yeah, it does agree, I think. Yeah. Of course, these are, 0 times z is less than or equal to 14. So we just forgot these, they don't do anything. Because the right sides are non-negative. If one of them were negative, then that would signal for inconsistency. But we do have a consistent problem here. All right, so with this, z is going to be less than or equal to 46 over 3. Also, z is less than or equal to 18. And the smaller of them gives you z star equals 46 over 3. Minus, sorry. The other one is also like that. So greater or equal. Yes, greater or equal. So the upper bound that's effective is minus 46 over 3. Then you substitute that, And then you solve for x2. As I said, in this case, x2 star will turn out to be 14/3. And x1 star in the original system will turn out to be 4/3, as far as I remember. Because I solved this on the side using graphical methods, and this is what you should get. If we're not getting that solution, we did some mistake along the way, possibly. Okay? Any questions on Fourier-Motzkin elimination? Okay. There's one question raised by one of you during the break, which is a valid question, which I did not really wish to go into. You can work that out on your own. This is the question. What happens at some stage of the elimination process? I'm trying to eliminate a variable, but it has, say, only plus coefficients and maybe zero coefficients, no negative coefficients. So if that happens, you don't eliminate that. You leave it to the end. Okay? You find a variable to eliminate which has pluses as well as negative coefficients. So you can work out the elimination procedure. So you keep eliminating the variables as long as there's a variable to eliminate. You keep going. And at some stage, you may not be able to proceed any further. That will be the case either when you have a single variable, in which case you start doing something else, or you don't have a single variable, you've got a bunch of variables, but none of them are eliminatable. Meaning that each variable in the last system has either pluses as coefficients and zeros possibly, or all negatives and zeros possibly. That case signals for either a trivial solution or an infeasible situation. I think you should work that out on your own. Okay? You should be able to do that. It's not difficult. And I explained to your friend during the break how that can be done. You should be able to work that out. That might be a good exam question too, maybe. You never know. The easy way is if you just think of a single variable that has, say, only pluses and zeros, okay? And you've got your right-hand side vector here. Now you've got a bunch of numbers and you've got all plus coefficients here. Now this part with the zero coefficients, however many you've got no negatives here. First of all, you want this part to be non-negative. Otherwise, there is no solution. Okay? If there's a negative number here, you have no solution. Now over here, by choosing your variable, say whatever it is, say suppose that's xn, and you want to achieve this situation, you want to make xn as small as possible so that a plus coefficient times xn, the left side becomes smaller and smaller. The smaller you make xn, these are not non-negative variables. These are just variables. So you can assign a negative value to xn, as much negative as you wish. Okay? All right. When you do that, this part will become negative. What about here? Can I, regardless of the signs of the right-hand side, can I obtain a feasible solution if this part is okay? Yes or no? For example, if my right sides are 2 and 3, my left sides are x, the last one is xn, and 2xn. You've got this situation, which means xn will be less than or equal to 2, xn will be less than or equal to 3 over 2, 1.5. So in this case, you've got only upper bounds, and obviously xn is only bounded above by 1.5, so you can make it as small as you wish. Okay? There's always a solution. How about if this guy is minus 3? Do I have a solution? Then in that case, xn will be less than or equal to minus 1/2. Can I choose? Sure. Just choose it, something less than or equal to minus 1.5. Okay? There's always a solution. So if there's a single variable with only this type of coefficients, you know what to do. Okay? If you've got other columns here with either negatives or positives only, you should be able to also work out the same kind of situation. Okay? All you are worrying about is to make the left-hand side as small as you wish, so that whatever constants you've got, the left side will be less than or equal to those constants on the right. That's all. Okay? You should be able to work that out. All right, I conclude the Fourier-Motzkin elimination at this point. Just one out of curiosity, maybe some of you may be wondering about this. When you eliminate variables, actually what you're doing is you're projecting one feasible set at the very beginning. If you think of it as a, some kind of a set in, say, n dimensions, you're taking the projection of that into the space of x2 through xn with one variable eliminated. So it casts a shadow on the space of the remaining variables. That's the projection, in case you understand what I'm talking about. Okay? Pictorially, pictures always help. All you're doing is the following. Let's assume we have only two variables, and we have a feasible set that may look like this. So inside of this, this is the x1 variable, this is the x2 variable. If I'm eliminating x1, what am I doing? I'm taking, actually, let me in fact, anyway, yeah, let's make it this way. I'm taking the shadow of this on this space, on the space of x2 alone. What is the shadow? The shadow is the set of all x2 values you could obtain from points inside here. Okay? And so you could obtain 0 and any of these values. You could also go up to here, because there's a point here that will give you that. So you reduce your feasible set from the initial one in the x1, x2 space to this shaded region along the x2 axis. That's the feasible set of your second system with x1 eliminated. And then you keep doing this. Well, in this example, there's nothing more to do, but that's the way we go. Okay? Now, we're going to continue with some geometric ideas, convexity and so forth, some foundational material. How many people have had anything on convexity here? Raise your hands. At what course? For example, Elif. In what course did you have convexity? In what course did you cover convexity to some extent? Say that again. 505, you've gone into some convexity analysis? Okay, good. Also, in undergraduate, I talk about convexity to some extent, but not everybody takes my session, so, I don't know. Some of you. Nonlinear programming, yes, but that was a special course. You took it only, yeah. Also, you guys, yeah. Now, how many people have no idea of what convexity means? Raise your hands, because I have to adjust my speed accordingly. Oh, you all know some. At least you have some idea of what concept convexity is. Okay, fine. So we may go a little bit faster. Okay, we'll deal with convexity both in terms of convex sets as well as in terms of convex functions. Let's begin with convex sets. I'm going to talk about points in the n-dimensional space denoted by Rn. That's the set of n vectors, okay, with the Euclidean norm. All right, so my points are in n dimension. Let x and y be 2 points in Rn. And lambda be a number in the unit interval 0, 1. You just pick 2 points and one number between 0 and 1, possibly including 0 or 1 as well. If you take the first one, multiply it with lambda, and take the second one, multiply it with 1 minus lambda, you're adding a scalar multiple of the first vector to a scalar multiple of the second vector, so the addition gives you another vector. That will be a point in Rn. And that's called a convex combination of x and y with weight lambda. Okay? So this new point is, the entire thing, is a convex combination of x and y. Okay? Now, pictorially, what's happening is the following. If x is here, y is here, say, in 2 dimensions. Origin is somewhere here. If lambda equals, for example, 1/3, it's a number between 0 and 1, then you get a point somewhere here in the middle. This is the point lambda x plus 1 minus lambda y, corresponding to lambda equals 1/3. Okay? Where this portion, if you think of a line segment between x and y, this little segment between the new point and y is 1/3 of the length of the entire segment. Okay? The other part is 2/3. Why is it 1/3? Because you can also think of a convex combination in the following way. Lambda x 1 minus lambda y is the same thing as lambda into, so what is this? Y plus lambda into x minus y. You may think of it this way. In which case, of course, when you take x here, y here, for example, the x minus y vector is which vector? Which one is it? Is it the one that points this way or that way? That way, right. It's this vector, except that the vector should be at the origin, but just for illustration purposes, I'm showing it like this. Okay? The actual vector, if this is the origin, looks here. Shows up here. That's x minus y. So let's just write x minus y on top of that. They should be parallel. Okay? All right, so all you're doing is you're taking y, adding to it 1/3 for lambda equals 1/3. You're adding to it 1/3 of the length of this x minus y vector. So this is going to be your lambda x minus y plus y. Okay? That's why it's 1/3. All right. If I pick lambda to be any number rather than a number between 0 and 1, but still I'm using lambda x plus 1 minus lambda y, then I still get a combination. But what kind of a combination? It's no longer a convex combination. Yes? It's not linear. A linear combination is if you have any real number here, say a1x, and b1, another real number, b1y, that would be a linear combination, okay? Any real times the first vector plus any real times the second. Affine combination, yes. If lambda is any real, then lambda x plus 1 minus lambda y is an affine combination of x and y. Okay? Good. So, lambda 1, lambda 2 are arbitrary two real numbers, then lambda 1x plus lambda 2y. In this case, there is no restriction on how you choose lambda 2. In the other cases, lambda 2 has to be 1 minus the first one. Okay? In this case, this is a linear combination. Which one gives you more choices, the most choices? Of course, the last one gives you many different. The output of this could be any, just about any. Okay? Whereas the other ones are more restrictive. Okay. The line segment between x and y, both are points in Rn, is the set of all convex combinations of x and y. So, if I denote just temporarily the line segment between x and y by, say, L of x and y, it's the set of points U in Rn such that U is some convex combination of x and y for some lambda in the unit interval. Okay? So any U that can be so obtained is in the line segment. Which means that if x is here, y is here, a particular choice will give me a point, something like this. Whereas if you consider all such points, of course you start generating all such points along the line segment connecting x and y. So, all points here. What about the affine combination? If A is the set of points x and y defined by U in Rn, where again U is equal to lambda x plus 1 minus lambda y, where lambda is some number in the real line. And in that case, the picture is a little bit different. When lambda is restricted to these points, you generate the line segment between them. But then, when you start picking lambda outside of the interval, you generate these points as well as these points. So this is the line passing through x and y. One is a segment, the other one is a line. It extends to infinity in both directions. Okay? What's before the theorem? I should tell you what a convex set is. A set S in the n-dimensional space is a convex set if the line segment, in the sense I defined it here, okay? If the line segment connecting any 2 points x and y of the set S is contained in S. By the way, the points x and y could be identical. X equals y is certainly permitted, okay? In which case, the convex combination will also output the point itself. All right, so that is, S is convex if for every xy in S and for every lambda in 0, 1, the point lambda x plus 1 minus lambda y, your convex combination is also in S. The second one is more mathematical. You know, it's more compact. The first one is plain English. Okay. So here's a convex set, because if you pick the inside of the set, if you pick any 2 points, x and y, and look at the line segment between them, it lies entirely within the set. And this is true for any choice of x and y. So this set is convex. If you look at this set is not convex, because if you pick your 2 points somewhere here, yes, the line segment lies inside the set. But if you pick 1 point here, another point here, it does not, the line segment connecting x and y does not entirely lie within the set. The dotted portion is outside. So this is not a convex set. How about the set S defined by the set of points in Rn whose norm is less than 1? Is that a convex set or not? God only knows. Well, I know what it is, but you have to apply the definition or something, some theorem known from convexity. But this kind of a set, if you take n equals 2, for example, this will give you, this is the origin, it will give you a disk around the origin whose radius is this constant 1. Except that the points on the boundary are not included because we've got a strict inequality here. Okay? So we're talking about the interior of the disk shown in the picture. Is that a convex set? The answer is yes, but by inspection it is convex. Okay? How about the set, for example, defined by essentially the same thing, except that I have greater than 1 now. Now this time, of course, we've got the same disk. The boundary is still not included. The points that are included are those points outside. Okay? So there's a hole around the origin of radius 1. And this set is surely not convex. For three-dimensional case, of course, the disk you have without the boundary is a sphere without the boundary. The surface is not included. And in higher dimensions, it's a hypersphere. That's what people term it. Okay? These are just straightforward results. One is the following. If S1 and S2 are two convex sets. By the way, the empty set by convention is convex. Okay? You might want to take a note of that. If S1 and S2 are two convex sets in n-dimensional space, then their intersection, S1 and S2, is also a convex set. The proof is straightforward. Let's just define S to be the intersection. So you just apply the definition. You say let x, y be 2 points in S and lambda be a number between 0 and 1. And then you question if the convex combination of these 2 points with that lambda is in the set or not. It should be. Okay? So consider the point obtained by this choice. Why should I conclude that that point is also in S? So
therefore, it's, this point is in S1 and S2. So 6 and Y is also in S1 and S2.
oh, I see. Okay. This point is in S1 due to convexity of S1 and is also in S2 due to convexity of S2. Görkem, this is what you're saying, right? Hence, this point, because it belongs to S1 and S2 at the same time, belongs to the intersection. That's it. Good. Can you extend this to any denumerable collection of convex sets? Yes, the answer is yes, because if you have a denumerable number of convex sets in the n dimension, you can take the first two, the intersection is a convex, and then remove the first two and put in the new one, and then work it out with the new one as well as one of the old ones, so on and so forth. So by induction, you see that you will always get the convexity regardless of the number of sets under consideration, as long as they are countable. Okay? Let's also talk about the level sets. Before I talk, okay, let's see. Before I talk about level sets, I need to define convex functions. So let me just define a convex function first. All right, the functions could be defined from any set into any set. The functions I'm going to talk about are numerical functions. In other words, the range is the real line. Okay, the domain is any subset of the n-dimensional space. Okay, where n is any positive integer. So we talk about convex functions with domain and range, where these are numerical functions, where the domain is a subset of Rn for any n and the range is and is a subset of the real line. Okay, numerical functions. Okay. So even if I don't say even if I don't use the term numerical, you should understand that every function I'm talking about is a numerical function. Okay. All right. A numerical function f is said to be. I should add a statement here. A numerical function defined on a convex set S in Rn. So the domain of definition is S, and it is assumed to be convex. A numerical function f defined on a convex set S in Rn is said to be a convex function if for every choice of points x and y in the domain and lambda for every goes for both x, y as well as lambda. Okay. Lambda in the unit interval 0, 1. The value of f evaluated at the convex combination lambda x plus 1 minus lambda y is always bounded above by the convex combination of the numerical values assigned to x, f of x, and 1 minus lambda f of y. Okay? So, this definition says whenever you take 2 points in the domain and some lambda between 0 and 1, when you find the convex combination of those 2 points, that's a new point, you evaluate the function f, you get a number. On the right side, you first evaluate f at point x, and then you evaluate y at point y, and then you take the convex combination of the evaluations, the functional outputs. Okay? So, for a one-dimensional example, if your function looks something like this, with x here, f of x on the vertical axis. So in this case, my domain for the function is the real line. Okay, the domain of function f is the real line, and the range is also a real line. Okay. So if I pick an x here, and pick a y here, and pick a lambda, then I generate a point such as this one. Okay? So when I evaluate my function at that point, I get the value here. This is my f of lambda x plus 1 minus lambda y. That's the value I get, the height of this point. Okay? So the left side is here. That's my left side in the definition. What is my right side? For the right side, I evaluate x first, f of x, which is somewhere here. That's f of x. And then I evaluate y, and I get this number. And then I get the same lambda combination between f of x and f of y, which gives me something here. So that's lambda f of x plus 1 minus lambda f of y. Okay? So make sure you understand where these numbers show up. Okay? And then you look at this point here. What point is this? And what point is this? What point is this, first of all? That's the point whose x-coordinate is lambda x plus 1 minus lambda y. What is the y-coordinate? I mean the f of x coordinate, the second coordinate. It's f of that point. No. F of lambda x plus 1 minus lambda y. Because this graph is the set of two tuples x and f of x, with x ranging in the, or changing in the domain. Okay? All right, it's that point. What about this point? What point is this? You've got the same abscissa here, lambda x plus 1 minus lambda y. The second component, or the second coordinate, is lambda f of x, lambda times f of x, plus 1 minus lambda times f of y. Let me erase this stuff from here. So you can see that the new point, or the point that corresponds to the right-hand side value, except as a point, is on or above the other point, the left-hand side. Okay? This is for a particular lambda. If you look at each possible lambda, you get this chord connecting the endpoints corresponding to x and y with their functional values. So this chord overestimates or is on or above the actual functional values. That's the picture you would probably remember, except that you should really understand what's going on here. Okay? Without that, I do not want jumping into conclusions, because that's what happens. If you start jumping into conclusions without fully understanding something, then you're bound to make a mistake, usually. Okay, so everybody understands this, I guess. I think we should be, we stop here. And on Wednesday, you are going to have your second recitation hour for the second problem set.